Welcome back. In this session, we derive and use the formula for center of curvature when the curve is given by a Cartesian equation. We also discuss the evolute of a curve, which is the locus of centers of curvature of points on a curve. We first discuss center of curvature and circle of curvature. The center of curvature at any point P of a curve is the point which lies on the positive direction of the normal at P and is at a distance rho from it. The circle whose center is the center of curvature and the radius is rho is the circle of curvature for P. Finding center of curvature. Let y is equal to f of x be a curve and P with the coordinates ordered by xy be a point on the curve where the radius of curvature is rho of P. Let the center of curvature C has the coordinates given by uppercase letters ordered by xy. We are going to express x and y in terms of the coordinates x and y. For this, we draw the circle of curvature at the point P with coordinates ordered by xy with its center C in uppercase letters x and y. Let psi be the angle made by the tangent at P to the curve with respect to the positive direction of the x axis. Draw perpendiculars from the points C and P to the x axis and let them meet the x axis at the points L and M respectively. Then draw perpendiculars from P to the line segment CL that meet at the point S. From the figure, it can be seen that angle PCL is equal to psi. Also, uppercase letter X is equal to OL, which is equal to OM minus LM, which is equal to X minus SP, which is equal to X minus rho of P times sin psi, and uppercase letter Y is equal to LC is equal to LS plus SC, which is equal to Y plus rho of P times cos psi. We know that rho of P is equal to 1 plus y1 square all raised to 3 by 2 all divided by y2, where y1 is equal to dy by dx and y2 is equal to d square y by dx square, where the values are evaluated at the point P. Also, tan psi is the slope of the tangent to the curve at the point P. Hence, tan psi is the same as the value of y1 is equal to dy by dx evaluated at the point P. That is, tan psi is equal to y1 evaluated at the point P. Thus, cos psi is equal to 1 upon sec psi, which is equal to 1 upon square root of 1 plus tan square psi, which is equal to 1 upon square root of 1 plus y1 square, and sin psi is equal to cos psi times tan psi, which is equal to 1 upon square root of 1 plus y1 square times y1, which is equal to y1 by square root of 1 plus y1 square. Hence, rho of P times cos psi is equal to 1 plus y1 square all raised to 3 by 2 divided by y2 times 1 by square root of 1 plus y1 square is equal to 1 plus y1 square all divided by y2, and rho of P sin psi is equal to 1 plus y1 square all raised to 3 by 2 by y2 times y1 by square root of 1 plus y1 square, which is equal to y1 times 1 plus y1 square all divided by y2. So, uppercase letter X is equal to x minus rho of P times sin psi, which is equal to x minus y1 times 1 plus y1 square divided by y2, and uppercase letter Y is equal to y plus rho of P times cos psi, which is equal to y plus 1 plus y1 square by y2. So, the center of curvature C with the coordinates in uppercase letters x and y is given by the formula ordered by uppercase letter x and uppercase letter y is equal to ordered by x minus y1 times 1 plus y1 square by y2 comma y plus 1 plus y1 square by y2. We once again note that the center of curvature and the circle of curvature of a given curve depends on the point P, but for a circle the center of curvature is same at any point on the circle and is the center of the circle itself. Also, the circle of curvature at any point on the circle is same and is the circle itself. Now, as an example, we find the center of curvature at the point ordered where CC to the curve xy is equal to c square. We write the given equation of the curve xy is equal to c square into the form y is equal to c square by x. Differentiating with respect to x, we obtain y1 is equal to dy by dx, which is equal to negative c square by x square. Differentiating once again with respect to x, we have y2 is equal to d square y by dx square is equal to d by dx of dy by dx, which is equal to d by dx of negative c square by x square, which is equal to 2 times c square by x cube. So, at the point ordered where CC, y1 is equal to negative c square by c square, which is equal to negative 1, and y2 is equal to 2 c square by c cube, which is equal to 2 by c. Hence, at the point ordered where CC, we get ordered where uppercase letters x and y is equal to x minus y1 by y2 times 1 plus y1 square, comma y plus 1 plus y1 square by y2 is equal to ordered pair c minus negative 1 times 1 plus 1 square divided by 2 by c, comma c plus 1 plus 1 square by 2 by c, which is equal to ordered pair 2c 2c. That is, the center of curvature at ordered pair CC to the curve xy is equal to c square is ordered pair 2c 2c. We now discuss evolutes and involutes. The locus of the centers of curvature of all points of a given curve is called the evolute of that curve. If the evolute itself be regarded as the original curve, a curve of which it is the evolute is called involute. Since the center of curvature at any point of a circle is the center of the circle, it follows obviously that the evolute, which is the locus of centers of curvature, is the single point which is the center of the circle. If we consider this center as the original curve, the involute is the given circle. We now discuss the way of determining evolutes. Evolute of a curve is the locus of the centers of curvature ordered where uppercase x and uppercase y of all points of a given curve. So, to find an equation of the evolute of a curve, we eliminate small letter x and small letter y from the following system of two equations. Uppercase letter x is equal to x minus y1 times 1 plus y1 square by y2, and uppercase letter y is equal to y plus 1 plus y1 square by y2. As an example, we first find the coordinates of the center of curvature at the point P or with the coordinates x and y on the parabola y square is equal to 4ax, and then find its evolute. Differentiating the equation y square is equal to 4ax with respect to x, we obtain 2y times dy by dx is equal to 4a. So that y1 is equal to dy by dx is equal to 4a by 2y, which is equal to 2a by y. Differentiating once again with respect to x, we have y2 is equal to d square y by dx square, which is equal to d by dx of dy by dx. Now, we use the chain rule of differentiation and obtain y2 is equal to d by dy of 2a by y times dy by dx. Since d by dy of 2a by y is equal to negative 2a by y square, the above gives y2 is equal to negative 2a by y square times 2a by y, which is equal to negative 4a square by y cube. Hence, uppercase letter x is equal to x minus y1 by y2 times 1 plus y1 square is equal to x minus 2a by y by minus 4a square by y cube times 1 plus 2a by y whole square, which is equal to x plus y square plus 4a square by 2a. Again, since y square is equal to 4ax, the above gives uppercase letter x is equal to 2ax plus 4ax plus 4a square by 2a, which is equal to 3x plus 2a. We call it equation number 1. Also, uppercase letter y is equal to y plus 1 plus y1 square by y2, which is equal to y plus 1 plus 2a by y square by negative 4a square by y cube, which is equal to y minus y times y square plus 4a square divided by 4a square, which is equal to negative y cube by 4a square. We call it equation number 2. Hence, the center of curvature C in uppercase letters x and y is given by ordered where x y is equal to 3x plus 2a comma minus y cube by 4a square. Next, to find the evolute, we have to eliminate lowercase letters x and y from equations 1 and 2 above. Squaring equation 2, we obtain uppercase letter y square is equal to minus y cube by 4a square all square, which is equal to y raised to 6 by 4 square times a raised to 4, which is equal to y square all raised to 3 all divided by 4 square into a raised to 4, which is equal to 4ax all cube by 4 square times a raised to 4, which is equal to 4 cube into a cube into x cube all divided by 4 square times a raised to 4, which is equal to 4x cube by a. From equation 1, we obtain that lowercase letter x is equal to uppercase letter x minus 2a by 3. Substituting this in the value of uppercase letter y above, we obtain uppercase letter y square is equal to 4 by a times uppercase letter x minus 2a by 3 all cube. A simplification yields 27a uppercase letter y square is equal to 4 times uppercase letter x minus 2a all cube, and this equation gives the evolute of the parabola y square is equal to 4ax. It is a common practice that instead of uppercase letters x and y, we use lowercase letters. Hence, the evolute of the parabola y square is equal to 4ax is 27a y square is equal to 4 times x minus 2a all cube. We now discuss a property of the evolute. Theorem: the normal at a point to a curve is the tangent at the center of curvature to its evolute. We now give the proof. Let p prime xy be the center of curvature and rho of p be the radius of curvature of a point p with ordered pair xy on the curve. Let psi be an angle made by the tangent at p to the curve with respect to the positive direction of the x axis. Then, by the discussions in the previous sessions, we have uppercase letter x is equal to x minus rho of p sin psi and uppercase letter y is equal to y plus rho of p cos psi, where rho of p is equal to ds by d psi, sin psi is equal to dy by ds and cos psi is equal to dx by ds. For convenience, we take rho is equal to rho of p. then uppercase letter x is equal to x minus rho times sin psi and uppercase letter y is equal to y plus rho cos psi. Now, we differentiate uppercase letter x is equal to x minus rho sin psi with respect to x. For this, we note that by the chain rule of differentiation, d by dx of sin psi is equal to d by d psi of sin psi times d psi by dx, which is equal to cos psi times d psi by dx. By the product rule of differentiation, d by dx of rho sin psi is equal to d by d psi of sin psi times rho plus sin psi times d rho by d psi, that is equal to rho cos psi times d psi by dx plus sin psi times d rho by d psi. Since rho is equal to rho of p, which is equal to ds by d psi, and cos psi is equal to dx by ds, we have d by dx of rho sin psi is equal to ds by d psi times dx by ds times d psi by dx plus sin psi times d rho by d psi. By a rearrangement, we obtain ds by d psi times dx by ds times d psi by dx is equal to ds by d psi times d psi by dx times dx by ds. Now, by the chain rule, ds by d psi times d psi by dx is equal to ds by dx. Thus, ds by d psi times dx by ds times d psi by dx is equal to ds by dx times dx by ds. Again, by the chain rule, ds by dx times dx by ds is equal to ds by ds, which is equal to 1. Thus, we obtain d by dx of rho sin psi is equal to 1 plus sin psi times d rho by d psi. Hence, dx by dx is equal to 1 minus 1 plus sin psi d rho by d psi, which is equal to minus sin psi d rho by dx. We call it equation number 3. Similarly, differentiating uppercase letter y is equal to y plus rho cos psi with respect to x, we obtain dy by dx equal to cos psi d rho dx. We call it equation number 4. From equations 3 and 4, we obtain dy by dx is equal to dy by dx by dx, which is equal to cos psi times d rho by dx all divided by negative sin psi times d rho by dx, which is equal to negative cot psi. We note that since tan psi is the slope of the tangent to the original curve at p, the slope of the normal p prime to the original curve at p is negative 1 upon tan psi, which is equal to negative cot psi. Also, dy by dx is the slope of the tangent to the evolute at p prime. Hence, from equation 3, the slopes of the two lines which have a point p prime in common are equal, and as such they coincide. Thus, the normals to a curve are the tangents to its evolute. This completes the proof. In this session, we derived and used the formula for center of curvature when the curve is given by a Cartesian equation. We had a discussion on the concept of the evolute of a curve. Also, the concept of involute is given. In the coming sessions, we will extend the discussions to parametric curves and polar curves. See you next time. Have a great day.